Okay, let's see test 13. Question number 1. Your physical education teacher throws a baseball to you at a certain speed and you catch it. The teacher is next going to throw you a medicine ball. The medicine ball is a ball, the big ball that sometimes used in the exercise, okay, or the aerobic exercise. A medicine ball whose mass is 10 times the mass of the baseball. You are given the following choices. Which one is the easiest to catch? Okay. The point is that what is the condition of the easiest to catch? In this case, we may say that the condition for the easiest to catch is that the condition for the minimum change of the momentum. Why we say that? It is because if we related the momentum with the force and the time, okay, if we related the momentum with the force and the time, if we apply force F to an object at the time interval delta t, we know that the momentum change is equal to the impulse, is equal to the F time delta t. Okay, so if you say that the ball can be easily catched, it means that it uses the minimum value of force or the minimum value of time or both, right? So it means that we want the minimum value of F or the minimum value of T to catch the ball. It means that easy to catch. So it means that the condition is the minimum value of the impulse or the minimum value of the change of the entropy of the momentum. Sorry, the change of the momentum. Okay, so let's see what is the condition for the minimum change of the momentum. A, the medicine ball throw with the same speed of the baseball. So you can see that the initial speed, initially the ball moves with velocity v and then it stops. So the change of the momentum is minus of the initial momentum, right? But anyway, we are interested only in the magnitude of the change of the momentum. So in the case A, we have the change of the momentum is mv, and for the case B, the change of the momentum is a capital mv. In this case, they have the same speed v, so we have that the magnitude of the change of the momentum of the medicine ball is larger than the change of the momentum of the baseball. It means that to catch the medicine ball is harder than to catch the baseball. Okay. Choice B, they throw with the same momentum, so the change of the momentum are the same. Okay. Choice C, they throw with the same kinetic energy of the baseball. The medicine ball is thrown with the same kinetic energy as the baseball. We can show that the relation between kinetic energy and the momentum is that the kinetic energy is equal to the momentum square over 2m. Okay, following this calculation, k is equal to the half of mv square. But if we multiply m on and above and below the ratio, okay, so we have mv square over 2m is equal to k, but we know that mv is p, so we have that k equal to the p square over 2m. Rearrange this relation, we have that p equal to the square root of 2m k. This k is the kinetic energy. So you can see that if the ball and the baseball and the medicine ball have the same kinetic energy, the one with the larger mass will have the larger momentum. So in this case, the medicine ball will have the larger momentum, and to stop the medicine ball, we need more force or more time, because we need to change more momentum than in the case of the baseball. So you can see that the case that we can stop the medicine ball, the easiest way is the choice B. They throw with the same momentum. Okay, so that is for the question number 1. For the question number 2, imagine dropping a ball at a high edge from the surface of the earth. By Newton's third law, the earth experiences an upward force and therefore an upward acceleration while the ball falls. At the instant that the ball of mass mb falls downward with the speed vb, and the earth of mass me moves upward with the speed ve, what is the ratio of the kinetic energy of the earth and the ball? Okay. From this, we have the third law of motion. The force exerted on the ball from the earth is equal to the minus of the force exerted on the earth from the ball. This minus term say that the direction of these two forces are in the opposite. And if the duration of these two forces acting on each other is delta t, if we multiply this delta t on the both sides, we have that the change of the momentum of the ball is equal to the change of the momentum of the earth. But the minus sign say that the direction are different. So if we are interested only in the magnitude, we have that the magnitude of the change of the momentum of the ball is equal to the magnitude of the change of the momentum of the earth. Now, we know that we assume that both ball and the earth start from rest, so it means that initial momentum is 0. So the change of the momentum of the ball is equal to the final momentum of the ball, and the change of the momentum of the earth is equal to the final momentum of the earth. And we are interested in the magnitude only, so we have this relation. Okay, and from the previous question, we know that the kinetic energy is equal to the square of the momentum divided by the 2 times mass of the object. So we have this is the kinetic energy of the ball, and this is the kinetic energy of the earth. Divided the second with the first, we have Ke over Kb equal to Mb over Me. Okay, so the answer is C. Okay, so that is for the question number 2. The question number 3, and 1,800 kilogram car stopped at the traffic light is stuck from the rear by a 900 kilogram car. The two cars become entangled, moving along the same path as that of the original moving car. If the smaller car were moving at 20 meters per second before the collision, what is the velocity of the entangled car after the collision? We can solve this problem using conservation of momentum. The initial total momentum is equal to the final total momentum. In this case, we have a big car of 1,800 kilogram first at rest, hit by a small car, okay, of 900 kilogram. This car moves with the velocity v, and the big car have the initial velocity equal to 0. After this event, both move together with the velocity vf. Okay, so from the conservation of momentum, we have the initial momentum of the system mv plus capital M capital V. In this case, this capital V is equal to 0, must equal to the M plus capital M times Vf. This is because they both move together. And put V, this capital V is 0, and the numerical value of this initial velocity of the small car, and rearrange this equation. We have Vf is equal to the mv over M plus capital M. Put the numerical value of the parameter, and we get Vf is equal to 6.67 meter per second. This is the answer. Okay. Question number 4. The question number 4. A block of mass M1 equal to 1.66 kilogram initially moving to the right. Okay, this one move to the right with a speed of 4 meters per second on the frictionless horizontal track. There is no friction on the floor. Collides with a light spring attached to the second block of mass M2. This is M2 of 2.1 kilogram initially move to the left with the speed of 2.5 meters per second. So if we take the positive direction to the right, this V2 has a negative sign, as shown in the figure. The spring constant is 600 Newton per meter. Find the velocity of M1 and M2 when the spring is at maximum compression. The key point of this question is that at the maximum compression, we have that M1 and M2 move with the same velocity, right? If they are not moving with the same velocity, it means that the situation is that they are moved closer or they are moved faster, right? And that means that the compression of the spring at that point is not the maximum compression, right? So we must have the condition that at the maximum compression, M1 and M2 move with the same velocity. Here we can consider this problem as a collision problem, and we can use the conservation of momentum in this case. Anyway, we know that at this point that we are interested, the spring has a maximum compression and they are both move with the same velocity. So from the conservation of momentum, the initial momentum of the system before the collision must equal to the momentum of the system when they are moving with the same velocity v. Okay, so we have this relation. Rearrange this relation. We have this capital V is equal to this term, and if we put the numerical value of this term, we get the value of capital V equal to 0.31 meter per second. This is the answer. Okay. Follow to the question number 5. Due to the previous question, find the maximum compression of the spring. Now, we want to know the maximum compression of the spring. Since there is no friction, they said this is on a frictionless surface. So, all of the force involved with this collision, the only force that involved with this collision is the force in the spring, which is the conservative force. So it means that we can use the conservation of energy to solve this problem. The conservation of energy states that this is the initial kinetic energy of the system. In this case, you can see that there is no potential because these two objects move in the horizontal plane. So the gravitational there is no gravitational potential. There is potential, which is the elastic potential, but there is no gravitational potential because this M1 and M2 move on the horizontal plane. So it means that the gravitational potential is a constant. We don't have to worry about the gravitational potential in this case. So we have that the initial energy of the system is the kinetic energy of M1 and M2. And when the spring has a maximum compression, the total energy of the system is the kinetic energy of the system plus the elastic potential of the system that comes from the compression of the spring. Okay, and if we rearrange this relation to solve for x, we have this, and we put the numerical value in this expression. We have the maximum compression x is equal to 0.5 meter or 25 centimeter. So this is the solution. Problem number 6. Two firefighters must apply a total force of 600 Newton to steady a hose that is discharging water at the rate of 3,600 liters per minute. Estimate the speed of the water as it exits the nozzle. Imagine that you hold a hose which discharge or eject the water, and you from experience we know that if the water moves fast, you have to hold the hose tight to steady the hose. So it means that when the water exits the hose, it will exert some force to the hose. And how come this force? Where is this force come from? We can understand this by looking at the general form of the second law. We know that the general form of the second law is F equal to the dP over dt. If we put P equal to mv, we have that F equal to the mdv by dt plus v dm by dt. Normally, if we apply the force to an object and object do not change the mass, this term go to 0, and we have F equal to mdv by dt, and dv by dt is nothing more than the acceleration of the object. So we have the familiar relation that F equal to ma. But we can have the situation like in this problem, that the velocity of the object does not change. The water that discharge from the hose go with the same speed, the constant speed. So the speed of the water does not change, but the mass of the water in the hose change all the time. So in this case, we have that dv by dt go to 0, and we must have F equal to v dm by dt. Force comes from the change of the mass, and when you push the object, when we put this object out of the hose, from the third law, the water, in this case the object is the water, will push back the force to the hose, and this force is 600 Newton. So we can equate the force of 600 Newton to the v times dm by dt, this term. Okay, and we know that dm by dt is equal to rho dv by dt. In this case, this v is the volume of the water. dv by dt is the rate of the volume discharge of the hose, which is equal to the 3,600 liters per minute. Okay, so when we put this dm by dt equal to rho dv by dt to this expression, we have F equal to v rho dv by dt, or rearrange for v, we have F over rho dv by dt. And when we put the numerical value F equal to 600 Newton, rho is 1 kilogram per liter. Since the unit of the volume here is liter, so we can use 1 kilogram per liter of the water, and this is 3,600 per minute, but we have to change this to per second, so we divide it by 60 from the 60 seconds for 1 minute, and we do the numerical calculation to get 10 meters per second. Okay, so the answer is B. Okay, so we have the solution for question number 6.